ChatGerry, example of a daily glucose energy calculation using a linear glucose model, number 1382, October 7, 2025. Gerald C. EclaireMD Foundation. Category, Diabetes. Overview. This study presents a simple and practical way to measure daily glucose energy, using a linear glucose model. It is designed for people using continuous glucose monitoring, CGM, devices and aims to quantify real-time metabolic stress through integration of basic principles, rather than relying on quarterly lab tests of hemoglobin A1C. The model converts 96 daily CGM readings, every 15 minutes, into normalized values and integrates them across 3 glucose zones: hypoglycemia, below 70 mg/dL, normal, 70-140 mg/dL, and hyperglycemia, above 140 mg/dL. Each reading contributes proportionally to the total energy area, representing both duration, x-axis, and intensity, y-axis, of glucose exposure. In physics terms, this model incorporates both frequency and amplitude, capturing how often and how strongly glucose waves fluctuate over time. Simplified linear model. Traditional models like the viscoplastic medicine theory, VMT, require multiple variables, blood pressure, weight, diet, and stress, to compute energy transfer. The linear glucose model removes these complexities, focusing purely on glucose itself. Instead of squaring glucose values or including stress terms, the linear approach directly integrates normalized glucose over time. This method captures the real metabolic load imposed by glucose fluctuations during one full day, offering a physics-based but patient-friendly view of energy stress. Example calculation, data of October 6, 2025, using 96 CGM readings collected every 15 minutes. Each value was normalized by dividing by 140 mg/dL, 1.0, is normal upper limit. The 24-hour data were divided into 3 energy zones, and integrated as area percentages. Results for the day were: hypoglycemia, 0.0% normal glucose range, 73.2% hyperglycemia, 26.8%. These results mean my glucose remained entirely above the low range. Excellent control, stayed normal for about 3/4 of the day, and entered hyperglycemia about 1/4 of the time, mainly after meals. Despite limited duration, the higher amplitude of post-meal spikes raised the total energy load significantly. A good example of how glucose stress depends on both height, amplitude, and time, frequency. Another clinical model, known as TXR, considers only the time factor without accounting for the impact of glucose amplitude. It includes 3 indices: TBR, time below range; TIR, time in range; TAR, time above range. Clinical meaning: this simple integration method reflects true daily glucose stress, something that hemoglobin A1C and fasting glucose cannot. It allows patients and clinicians to visualize daily metabolic effort, identify when and how glucose spikes occur, and take immediate corrective actions. The model highlights a key insight: 2 patients may have identical hemoglobin A1C values, but very different glucose energy loads. The one with wider swings endures higher oxidative stress and greater long-term vascular risk. Why it matters. The linear glucose model bridges mathematics, energy, and medicine. It combines the integration concept from physics with real biological data, transforming glucose curves into a quick estimation of glucose energy. It offers a clear and realistic way for patients to evaluate their daily metabolic balance, supporting personalized diabetes management and prevention of complications. Disclaimer: this content is provided for educational reference only, and does not constitute medical advice. No doctor-patient relationship is created. You may share this summary freely, but it must not be altered, edited, or republished as your own. All intellectual property rights and copyrights for this article and its related materials belong to the author, Gerald C.